Okay, so I'm going to briefly explain how we have historically done testing at wolfSSL for all of our products, but particularly for our marquee product, wolfCrypt and wolfSSL TLS stack that sits on top of wolfCrypt. Obviously, when you work in security software and in cryptography, correctness is extremely important for our FIPS certification and our DO 178 certification workflows. We have third-party laboratories that additionally evaluate and verify the correctness of our code. I won't be talking anymore about that process, but just suffice to say that all of the testing processes that I'm going to describe here lead into that further process. So I'll give you an overview of how we do testing and why we do testing. So it's the why first. So one of the reasons that we have a comprehensive and continuous integration testing strategy that goes way down into the weeds is that it's the only way we can work quickly. Another aspect of working in security critical infrastructure software is that we need to be able to respond to any new requirements or any defect reports, even if it's a system integration or related defect report, very quickly. And we pride ourselves on responding to problem reports in a matter of hours. We typically have fixes for any identified defects merged within 48 hours, which is the best in the industry. The fact that we have continuous integration and very comprehensive nightly testing going on gives our customers confidence that our products will do what we say they do, and it keeps technical debt out of our code. Keeping technical debt out is extremely important to us because we need to make certain that our release process is orderly and that we're going into it from a known and trustworthy starting point. It's possible if you don't do these things to wind up with a scramble when you're preparing a release. We don't do that, and we avoid it by testing everything as we go rather than at release time. And we have some supplementary testing we do at release time that I'll talk about later, but our mainline testing is all happening continuously. We have a strong emphasis on portability in our code base. We support many targets and many configurations, and that puts us in a situation where comprehensive testing of all of our targets and all of our configurations as we go before the code merges is absolutely crucial. And the testing is the only way to know that we are safe on portability. And our general rule of thumb is that we have what we test. If you're not testing your code as you go, it's very easy to discover that you've lost something you thought you had. And the worst time to discover that is when you're preparing a release, because you want your releases to be methodical and an orderly process, and you can only keep it orderly by testing as you go. So this is just emphasizing how we test as we go. This is our continuous integration strategy. It's a layered strategy. We test before things merge. We test after they merge. We test nightly on the fully merged and integrated code base very comprehensively. And as I mentioned, at release time, we have supplementary testing. And one of the nuances here is that continuous integration testing doesn't actually tell you whether your code will be correct after it's merged, because independent PRs can actually be making changes that interact with each other, but they're not detected when those PRs are tested independently. So it's absolutely crucial that we additionally, every night, and sometimes additionally during the day, we run full test runs that cover the resulting integrated code base. And we also update our tool chains continually, and the updated coverage from latest tool chains sometimes uncovers problems that weren't detected by older tool chains. So one of the things that we really want to, as much as possible, arrange for is that when the code is delivered to you, the customer, we want to make certain that it's passing your existing quality control processes without change. And there's few things that create the wrong impression more than having a flurry of warnings, even if the warnings are benign, even if it's just, cast warnings and things like that. We don't want those to be there. They are distracting, and they're just inherently cause for concern, even if ultimately they're benign. And as I mentioned, we have a vast variety of valid configurations and targets. And that makes it particularly challenging for us to make sure that the code that we deliver to you is functioning correctly and warning free from the outset. But that is our aim, and we usually do hit that mark. Here's a little bit more about how we hit that mark. So as I mentioned, we have this layered strategy. First, we have local testing by the engineers. We have a script that we call wolfSSL multitest that's here. And that makes it easy for the engineers to run pre-baked tests in a completely controlled environment locally before they even push the code in the first place. Then we have the continuous integration tests that are self-hosted. We do have to self-host some of our tests because it runs on unusual hardware, on embedded boards, unusual runtimes that don't exist in the cloud. And we want to run on ground truth silicon, not just on emulated environments. We use QEMU and QEMU system to test on a vast variety of alternate silicon, not just AMD 64 and ARC64, but there's still a necessity to test the code on true silicon, and we do that by self-hosting some of the tests, some of the automated testing. We have additional nightlies that are run out of locally and out of cloud-hosted nodes. And then we have the biggest run, the biggest locally hosted run of testing is this wolfSSL multitest running all of its known configurations. We're up to around 350 different test scenarios that it runs. That includes the kernel module testing, all of the different flavors of silicon, a huge variety of FIPS configurations, historical, current, and future FIPS configurations. Those are all tested in our nightly test. And then perhaps the most important capability that we gain with self-hosted testing is what I briefly mentioned earlier, which is we update to the latest kernel, the latest pre-release Linux kernels, the latest pre-release GCC, and the latest pre-release LLVM in order to get new coverage from the latest Clang Tidy, the latest static analyzer in GCC, the latest changes in the latest Linux kernel. And we also use the kernel sanitizer, the kernel leak detector in the latest kernel in order to get additional static and dynamic analysis coverage from our Linux kernel testing. And Gen 2, we use Gen 2 Linux in order to achieve this, just like Android internally is based on Gen 2 Linux at Google. We use Gen 2 in order to streamline updating our tool chains to the latest and greatest. Every day or two, we update to the latest kernels, the latest tool chains, and we're actually able to apply custom patches that work around bugs in pre-release software or add additional capabilities for us at the source code level in the analyzers. So I'll tell a brief story before I hand it over to Peter for the AI guided fuzz testing presentation he's going to give. One of the tricks with conventional static analyzers is that it's very easy to think that you know what you're testing, but you don't actually have the test coverage that you think you do. Analyzers, static analyzers particularly, are finicky. Our configuration for Clang Tidy and for CPP check, and honestly for the sanitizers also, is extremely complicated. It's evolved over the course of many years to make certain that we have everything switched on that can be switched on, and yet we have masked out the tests that give silly results. There's a lot of these readability tests are just noise for us, and we disable them. There are obviously few, if any, security implications for disabling some of these readability, like misleading indentation. We have other tests that flag indentation errors. So we cover these in different ways that are more useful for us. But even with all of that careful curation of our configurations of the static analyzers, there are still gaps. And I'll give you a very brief case study for one of those gaps. So back in January, we merged a fix for a null dereference defect in an error path that Clang Tidy had detected. When we merged that, unbeknownst to us, we had actually added a new memory leak defect, and none of our analyzers detected the memory leak. I believe Coverity may have detected it out of band. We run Coverity manually, and I think that's where we first detected it, which raised the question, how did that happen? So Clang Tidy and CPP check both have heap memory analyzers built in, and we expected to get a warning from them if we added an obvious leak where a pointer was being assigned a value returned by a heap allocation, and then was passing out of scope with no further action on that pointer. So what happened was that we shim, for portability purposes, we shim all of our heap access with names like xmalloc, xfree, etc. And when we did that shimming, we blinded both Clang Tidy and CPP check in their default configurations to their normal analysis of heap access patterns. And once we eliminated the shims for Clang Tidy and added a custom configuration for CPP check, we regained that visibility. We discovered several more heap memory defects and fixed those. And now we have it locked in, and no more surprises. But it's just an important lesson that with conventional static analysis, and to a lesser degree dynamic analysis, the configurations and the coverage are very brittle, and it's very easy to think you have a category of defect covered, but you don't actually have it covered. And that's a really good place to pass to Peter from Code Intelligence, who's going to describe how they use AI and fuzzing in order to detect defects without the brittleness and without the sort of preconceptions that are built into conventional static analysis. And with that, I'm going to hand it over to Peter, who is going to talk about what Code Intelligence does.
Hi all, let me just share my screen. Yeah, so I'm Peter from Code Intelligence. We are a startup based in Bonn, in Germany. And today I will tell you how we discovered a few things in wolfSSL. So yeah, we last year, in November, we found a heap user after free in wolfSSL. But the remarkable part about this isn't that we found it. The interesting part was that we found it without actually doing much. So these are the steps that we did. So basically, you modify 3 lines in CMake lists. We use the CMake integration in CMake build system from wolfSSL, and then run the command cifuzspark with some more arguments. But basically, that's about it. And then check the findings, and that was it, right? And and then when we were preparing for this webinar and met up, and then Daniel challenged me to find more bugs in wolfSSL. And exactly right after that meeting, I fired up cifuz, and we found 2 additional issues in wolfSSL that have already been fixed. It's not only that we observed this behavior in wolfSSL with our tool, we also did the same or experienced similar success in other open source libraries. So no matter what we start, we always find something. Basically, that's the message here. And since I see in the post that are quite, it's probably divided. The crowd is divided. Some people know what's fuzzing, and the other half knows about fuzzing, but has maybe not used it, and so on. So maybe it's a good idea to revisit what's fuzzing and so on. So there is fuzzing. As it started, it was a black box method. And basically, here on the right, we have system under test, and we bombard it with some random inputs, and then random inputs that we don't know what's happening. They might cause crashes, but we basically have no insight in what is tested, and we will miss a lot of bugs. So this is how fuzzing started. Actually, that monkey should probably use the rest of the keyboard as well. So it doesn't look uniform to me. And so now we come to Whitebox fuzzing, and this is it is similar to Blackbox fuzzing, but completely different and way more efficient. So we have here on the left side as well the fuzzer that is bombarding things. Somewhere in there, there's still the monkey doing random inputs, and then we still have system under test, but there is now a huge change in the system under test because now we instrument it. So you compile it with with certain flags that you know what you cover when you run the code. You use the sanitizers, for example, address sanitizer or unified undefined behavior sanitizer, so that you can actually tag bugs. And what is happening here, there is now a feedback loop coming from system under test. When you run it, you know what coverage it delivers, you know which lines of code have been covered. And if there is a crash caused by the sanitizers, you will detect it as well. And now the fuzzer can be way more efficient by changing or by reacting to the feedback and coverage it gets from system under test. And and now in the center, we have this thing called fuzz test or fuzz harness that actually there we select or we define which functions we want to test. And so it's not that easy to do. It's super efficient, but it's actually quite hard. And there are two parts that make it extremely difficult. The first one is which function do we start? So usually we have huge code bases. Like if you look at wolfSSL, it has, I don't know, 3,000 or 4,000 functions. Which ones do we start? Which ones are the important ones? And then the second part is, now that if we know, let's assume we know which functions are important, how do we write a fuzz test for that is efficient and actually is doing what it's supposed to be doing? And these two parts, they require a lot of manual work. That's why it's so hard. And so our idea is for these two problems is so we should probably focus on high impact functions. So some customers, they already know what are the critical functions, and they have a good idea of what they want to fuzz and what to test. But if they don't, a good idea is to look at complexity. And the idea behind it is the more lines of code there are, the more bugs there are. It's kind of correlated. And also, if we write a fuzz test for high complex functions, it means that we need to write less fuzz tests, right? The more, but then the more coverage we can reach from one fuzz test, the fewer fuzz tests we will need. Then the second part is, how do we write a working fuzz test? So as a pen tester, I would probably read the docs. I would check some examples, see how the function is supposed to be used, check the function itself. But that's a tedious process. And what we did with our software, so we developed a so-called AI test agent that automates these two parts. So basically, the first part where we select the targets, it's a solved problem because we can do static analysis, and that's what we do. We do static analysis of the code base, and we see we build up recursively how complex every function is. Then we sort the functions by complexity, and then we can start with the most complex one. Right? That's easy. So now to create fuzz tests, we can make use of the LLMs, and recently they have been getting much better. And what we do as well is so we combine the LLMs in this step with the knowledge that we have just done in the first step by analyzing the code base. Excuse me. So we combine the static analysis with the LLMs to create fuzz tests. But that's not all. So the third step is we can run the fuzz test as well and see if they run. If they don't run, we go back here, give the errors to the LLM. So basically, this is a feedback loop that tries many different solutions and fixes the errors, generates fuzz tests, and then after the fuzz tests run, you can actually check the findings and the coverage. And here's where the human is required. So when we found the wolfSSL finding, I actually manually checked if it was a real finding. So I didn't want to bother wolfSSL with some false positives, so I checked that as well in the other two findings that we found. So yeah, that's our solution. And maybe a few words about fuzzability of wolfSSL. So the good part about wolfSSL for fuzzing, or in terms of fuzzing, is that it has a large number of examples and tests, and the LLMs or our solution can use that and build very nice fuzz tests. The other good part about wolfSSL is they have super fast response time. As soon as you find something, they quite quickly confirm and fix the issue so that you can keep on fuzzing. And that's very important, because once you find something, you don't want to fix it yourself and fuzz when then wolfSSL fixes it differently, and then the new bugs that you find mightn't even be an issue anymore. So so that's the good thing about wolfSSL for fuzzing. The bad part, or let's say the challenging part, is that it's crypto, and you would usually expect very shallow coverage. If you just write a fuzz test for any function, probably you will get shallow coverage, and because it is a very highly structured data that is used in most of the functions. So if it is a certificate or some private key, they need to have certain structure, need to be generated correctly, and the fuzzer struggles with that. So this requires extra help. And some functions also make heavy use of the RNG. For example, if you want to establish a connection, SSL, TLS, you get challenge responses that contain random numbers, and they have to correspond to the responses and so on. So it's very difficult for a fuzzer to get this right. And yeah, so well, actually we come to the live demo, and it has several parts, because once we start the iTest agent, it actually needs to do some work before we can observe the results. So let's see first, what changes did I make to wolfSSL. So here's some master branch. Let me make this a bit bigger. So here on the right, it's just a git view of the CMake lists. Sorry, did not, it's down here, sorry. So we first did something sacrilegious. We made it a C++ library just for the fuzz testing. Then
we support that, Peter. That's actually a supported configuration. But it's deprecated, okay, I will say. No. The Clang actually deprecates that. But sorry, continue.
Yeah, no problem. Just chime in if you see something. That's cool. Yeah, so this is like the internal stuff that has to be there. We use CMake integration. We can also use the make build system, but it's a bit more complicated. The CMake works right away. So this is it. This line is added automatically by the iTest agent. Okay, so this is our own configuration. So basically what I did is I passed this to CMake so that we enable some more user settings, and I can also show you the user settings. Let me see. So basically, I don't know much about this user setting, so I'm not an expert in wolfSSL at all. But basically, I try to enable as many things as possible so that we see more of the complex functions and so on. So I think this too, they add a lot of complexity. The PKCS7, the SMIME, and so on, and a bunch of other things that I know nothing about, but I enable them anyway. And yeah, so this user settings. And yeah, another thing, I added the hints to the LLM. And so let me show you this as well. So this is what I added. I use this as hints because I configured it with user settings. I think you need to include this header in every fuzz test. Otherwise, the structures will have different sizes, and you will always get buffer overflows, even though you shouldn't. It's because you forgot to add these options. So right. So that's pretty much it. And let's see if we can generate some fuzz tests today. So here we are now in CFS Spark. I have already prepared some old fuzz tests in case nothing works, but let's see. So this is the CMake list, and here we have, so the CMake list is the one we added to the main CMake lists. And here we will see now some fuzz test configurations being added. And we can just run CFS Spark. Let's see what I have. And let me explain a little bit this command that I'm going to run now. So this is what our tool is called. It's a Spark. There's no AI test agent here, but that's basically the AI test agent. It's the code name for it. We want it to run for 15 minutes. I think that's enough, but we can cancel it at any time. And then I pointed to the hints file because the LLM should know to add that header to every fuzz test. And this is basically how many candidates, how many functions we want to fuzz, but we will never reach that number, but just in case we keep it there. It's also possible for other libraries to have, let me see which one. Ah, yeah, to specify the target coverage. So you can say maybe target percentage. If you want to have coverage of 60%, then you let it run. You let the iTest agent run until it reaches the 60% coverage. with the fuzz test. So it keep on generating fuzz tests and producing more coverage. Wait, let me clear this so it doesn't clutter the view. Fuzz Spark. So let's just run it. So while it's running, because now I already pre-compiled it, so it doesn't compile the library. Library was compiled, and we see that it found 3,127 candidates, right? And we let it run, and we check something else. We'll check what these candidates mean. So I'm now in another directory. It's because I don't want to interfere with the test agent that's running here. I'll switch to another folder, and here we can run CFS candidates. Candidates. Let's say we want 30 candidates. And this is a cool overview of our wolfSSL. So basically the most complex function, and this is what I've been talking about, that we did static analysis. Now here you can see all this data packed into very densely. It has a lot of information here. So let's maybe unroll it a bit. So here's the function name, wolfcrypt test main, right? And it has reachable. So from this function, you can reach 50,000 lines of code. This is what this means here, lines of code. We also check for complexity. So it's cyclomatic complexity, total cyclomatic complexity, then the dangerous expressions and so on. So it's explained here. But basically, we derive a score based on complexity of that function. And we print it here, right? And this is what the AI test agent does as well. It sorts all the functions based on complexity and takes the first one. But now the first one is a test. And it's actually quite cool that here you can see how many lines of code are reachable from that test. It's fascinating. So in the total code base, I think it has, at least what we see in coverage later on, it has like 120,000 lines of code visible in the coverage reports, at least for us. And this test reaches 50,000. So it's quite impressive to one test. So we have tests, but let's remove those tests from the. I will remove those tests. So because we don't want to write fuzz tests for tests, right? So we need to kind of exclude them. Here in that repository, I added this. So I remove all the examples. So it's a globe pattern. Remove the tests and benchmarks and so on, because we don't want to write fuzz tests for this. And how does this look like? So Daniel, what do you say is the most complex function in wolfSSL?
Oh, that's an interesting question. The OCSP stuff is probably some of the most complicated.
OCSP, maybe I didn't enable it. Do you have to enable it with a certain flag?
If you didn't do enable all, you were doing a CMake build. So in the autotables build, you may actually need to switch that on manually.
Okay.
I can't remember if we have an equivalent in CMake for enable all.
Let's do this. Maybe we can find it. OCSP, you say? OCSP? Yeah. Let's see if we find something like that. Okay. It doesn't look like complex. So maybe I didn't enable it.
Those must be disabled.
Okay. So, but what we do see is SMIME. So these are the complex functions that we see. The 30 most.
The SMIME, the PKCS7, or just all the PKCS stuff, anything that's hitting the ASN layer, that's going to be complicated.
Yeah. What do you think about the print function? Because I disabled the iTest agent to run fuzz tests with them. Because I don't feel anything about the print functions. I think they're like supposed to print something on command line.
Yeah, that's the type of stuff that we use. We actually use those in the testing a lot. Like the unit, the big unit.test, that's making calls for dumping X509 data to the terminal.
Okay, interesting. So it's good that I disabled it, and I can show it what I did. So
that's not that no real normal application would be using those. They're just dumper functions.
So it was a good idea. Yeah. Okay. Great.
Yeah.
So I also here
and TestWolf crypt was also. I mean, we actually used TestWolf crypt for fuzz testing and sanitizer scenarios and leak testing inside the Linux kernel. We run that entire program inside the Linux kernel. But no, it should not be a primary target for your fuzzing.
Yeah, right. So we disabled that. Okay. Yeah, cool. So here we skipped. So in the configuration where the iTest agent is running, I have skipped some candidates. So the print ones are disabled. I also have the same exclude, so we don't make fuzz tests for these things. Right, and we can already see what is happening here. So we have the output is also quite, maybe not complex, but we see the total coverage, right? The first fuzz test was written for wolfSSL as my right PKCS7, right? And then we see the total coverage, and we see that many lines of code. So we covered 310 out of 121,000 lines, and so on. This is the fuzz test coverage. So here the total coverage accumulates slowly from the lines of code that we see, and here's the individual fuzz test coverage. Maybe we can take a look into some of them. So let's see what we generated. So what was the first one? Let's take a look at this one. So the cool thing about this is that it's a running fuzz test, right? So it already runs, it generates coverage. You can take a look inside. If you want to modify it, you can always do that. If it does something that we don't like, we can always change it. So here we see that it followed our hints. It added the options.h. And here's the general construct. So we can, if you set up something once, you can add it here. It's some macro that we use. You can see, and here's the fuzz test. It boils down. So we use libfuzzer underneath, but we can also use other engines. And here's the fuzzer data that comes in. It has this size, right? And then what we do is we use fuzz data provider. It's also kind of packaged together with libfuzzer, that you can give it some bytes and get certain types out of it. And then what we see is where it's used. So we get some bio data out of it, and write it into the bio, and this bio is used somewhere here to sign something. The interesting part here is that it used null for sign cert and sign key. So this is something I would change, right? So it's a running fuzz test, but this is not optimal, right? I would now look at it and change it, because this is not how it's supposed to be. So if it's null, then it's not using any set, it's not using any key, and it shouldn't be like that. So I would probably use the same construct to have a bio and then pass it to the certificate and read it out. Let's maybe take a look at another one. So this one had much coverage. Let's see. So it's a similar construct. You see it again. Didn't forget options. So it actually follows the hint. Let's take a look. The fuzz data provider, consume data, write into p data. That's our buffer. How big is it? Okay. So what happens to p data? So it's basically checking, right? But the way I found the original bugs that we found in wolfSSL, it was more like I let it run for 3 hours and then come back and check the findings. Here we see findings, but we'll also take a look at the findings now, but don't worry about that. I have redacted, so you won't see details in case there are real findings. So let's follow the data further. What's happening here? Is this a good fuzz test? So we see now we consume the data into this p data. That's a lot of code, right? But still, we what do we do? Make a PKCS7 out of the data and give it a null. So it probably returns this. Let's check this. Is it supposed to? Okay, if it's null, it probably returns it, right? So let's go back. Let's go back. Right. So here we have a PKCS7 object that comes out. Right, so we get some fuzzer data inside, and what comes out is PKCS7, and we use it to verify something. We call the verify on it. Right, so it's not bad. So it's a good start, and it's running. It generates some coverage. In case I wanted to change something, I would do it. And the cool thing is I can rerun. Let's check this one that has a bit more coverage. So now you see how fast, like while we were talking, it already made 4 fuzz tests. Like basically, just can get a coffee in that time. So this fuzz test looks more like what I would expect from a nice one. So we again have our fuzz data provider structure, and we get cert and key and CA. And it's nice. It writes the data into the BIOS and actually reads the certificate, the signing key, the CIA certificate out of them. Let's see what it does with them.
Now you say rerun, Peter. Is it actually setting the wolfSSL randomness seed to the same value so that you get deterministic behavior out of the library?
So here no, and not in these functions. So what I mean by rerun, you can rerun and regenerate the fuzz test. So maybe we can check the logs, and I'll show you what I mean. So here you can see how the agent works. It's basically, it's a big log, but you can see like, so it's some analysis. Oh, yeah, here's some libfuzzer output. So this is the first fuzz test that we saw. It actually is running in the background and checking the coverage. And then if you don't like the fuzz test, if it doesn't look good, like the first one we saw, then you would go in and change. So you can change it yourself, but you can also rerun the AI test agent to regenerate this fuzz test in case you don't like it, right? But this one, for example, the one that we just checked, I actually like it because it gives me the data out of fuzzer data. It's connected, right? And then I can actually get the signing certificate from fuzzer data. This should be a valid signing certificate. And this is where the problem with coverage comes in, because the fuzzer will never generate you a proper certificate. So this needs some help. What I would then do, and because now I didn't have to write this fuzz test myself, I can go and spend some more time to increase its coverage, right? So I like this fuzz test. I would go here and actually write some data. So I did something similar recently for another library. I asked Claude to generate me a bash script that would pack me these things together and generate me actually seed corpus that I would then copy paste into the corpus. So we have here CI fuzz corpus. Every fuzz test has a corpus here, and you can copy paste it there. And then it would actually have proper certificates and keys, and they have I think they have to match. Otherwise, you will not reach any more coverage after this.
Yeah, that makes sense.
If they don't match, right? And then here's where they're used, right? You have the cert and you have the key, and there's some data in the bio. It actually takes the data, but it doesn't matter what's in this bio, I think. I already pre-checked these functions, what they do, right? So then we sign it, and if you have proper certificate and key, and they match, and then you can actually get very deep into this function. So that's what can be done. Actually,
and Peter, you must have had Claude also generate a certificate authority certificate so that it was a complete set of validatable data.
So what I did is I asked it to write me a bash script, exactly to use. So I use OpenSSL to generate these things. So I asked it to please use OpenSSL to generate me correct certificate and key pairs that I can use, and then pack them together. So the script should pack them together so the fuzzer can actually make use of them, right? So that's what I did.
Okay,
so it's manual work, but it's also like AI, and really it's super nice because now I have the time to spend it. It actually has
so you're using an LLM. It's all self-hosted for you guys, right?
So yeah, the LLMs that we use. So there are many ways to use them as long as you support the OpenAI API, and we also support the Bedrock, and you can deploy them on Azure. So we support these options, and it's easy to add an API. One colleague of mine has also Ollama running locally. So you can
we do that. We have Ollama. Most of the engineers at wolfSSL have Ollama running locally, actually.
Yeah. So this fuzz test I like very much. And you see here it does the tear down, so you don't get memory leaks in the fuzz test, which are super annoying. And you don't get the memory leaks because the fuzz test is actually run and checked. And if it sees, so if we see a memory leak, we say that the fuzz test is not good, and we try to regenerate it. So we give that error to the LLM, and it regenerates the fuzz test. So it's actually it's doing all the steps it's supposed to be doing. So this fuzz test I like really a lot. And so it does the setup, tear down. It even checks some flags here in the for loop. So it's pretty cool. And I didn't have to do anything. So I could, help it out with, because it's crypto. I mean, that's different, right? Most of the other libraries that are not crypto, they're a lot easier to have deeper coverage. But here's a special case, and yet we still could find something, right? So it's already something. So yeah, what else can I show? I think that's actually pretty much it. So that's while it's working. I think it rarely can generate for this function. So we can rarely generate fuzz test for this function. But maybe let's stop it here. So I will just stop it and see what did we find. So this is what I mean by redacted. I don't want to flash any findings if they're real, but I've done it many times when preparing for this webinar. So I expect they're not real ones. So at least this one out of bounds. Like the other ones, undefined behavior, I've seen some shifts and stuff like this, but I expect this from crypto. So to me, this is low target Like if I find something undefined, I have to understand the crypto, and I don't have time for this. So
No,
maybe we can
it
like
says,
see.
Peter, when it reports out of bounds, is that the UBSAN or ASAN sanitizer that reported an out of bounds, and that's just being displayed as the ultimate result of running the fuzz test?
So out of bounds is ASIN. So it's address sanitizer. Usually that's what happens.
Okay,
But,
yeah.
so
So
if
we
you want, we
see.
can check it.
No, let's leave it alone. I can tell you, we see a lot of, particularly with the static analyzers, we see a lot of false positives on out of bounds. So I'm
Hmm.
not surprised that that's popping up, and we have a slew of them that we have suppressed because they're just false, and it just seems to be something that's very difficult for the analyzers to get right.
Hmm. Right. So, so in this case, I mean, I would now, if what I would do, I would check these findings, right? I would check this finding. I would go into the fuzz test and see if the fuzz test is correct. And once you fix it, you will not have out of bounds anymore. In case it's, it's not a UB SAN, but a real ASAN, so address sanitizer issue, then you would fix it if it's in the fuzz test, right? Then you will not have it again. So that's easy, and then you can reuse it. The cool thing about fuzz test is you can let them run, and they will generate more coverage, generate better inputs, and get deeper and deeper the longer you let them run. So and that's like your capital. That's the value you can always reuse and reuse again. So that's the cool thing about fuzz testing. It kind of grows on you, with time. It gets better and better. And then when you fix the issue in the fuzz test, and you get a nice working fuzz test and increase the coverage. It's great.
Would you liken it to being like a genetic algorithm?
So underneath, libfuzzer uses genetic algorithms. So
Yeah.
it used some randomness, genetic algorithms, and then the old AI.
Yeah, so yeah, exactly. It evolves toward more and more comprehensive, asymptotically toward 100% coverage.
Yeah, that's right. Yeah. So what did you see here? So we could generate 6 out of 8 successful fuzz tests. This one failed. I prepared some old ones, but we have seen a nice one here, so we don't need to look at that. Right. So what else do we see? We have 6 findings, 3% coverage. I think I can go back to my slides and show you what happens after 3 hours. How does it look like? So this 160 findings detected, they're all undefined. There are so many undefined behavior findings in wolfSSL, so I just did not check them. So I focused on the buffer overflows. I focused on more interesting targets for me. And also when you have address sanitizer, you know right away if it's a buffer overflow, it's really a buffer overflow, and it's a wolfSSL issue if it's somewhere in the wolfSSL code. So it's nice, and it's easy to see that. But for the UB sign, so like shifts and stuff, I have to understand the crypto, so I didn't focus on them. But the cool thing also is that we have 114 successful fuzz tests now generated, and actually reached 15% coverage. And I'm not sure if the numbers that you've seen here, this 121,000 lines of code, if they're correct, because I know they're growing with time. The more files you see. So the LCAF report, it might be that you generate another fuzz test, and then suddenly this total number grows. So I'm not sure if how accurate is this, but let's say we get 15% coverage, and we used about 9,600,000 LLM tokens, and this is a combination of input and output tokens. So the output tokens are, I think, more expensive, but yeah, that's how much we used. So yeah, so if you like what you see, the next steps, if you want to try out a AI test agent, would be to get a CFS license and ensure that you have access to LLMs. So I've mentioned some of them. So you can use the OpenAI or Azure or AWS Bedrock, or even locally Ollama. That's also possible. So we don't control this. You can just point it to an endpoint, get the tokens, whatever you need to connect, right? And yeah, you can talk to us. And I think we have one more slide. If you want to know more about fuzzing, we also have a white paper on our webpage. Yeah, I guess that's it from my side. Thank you.
Thank you, Daniel and Peter. So there is questions. So we are moving on to Q&A session, and there's There's a question. Is the test setup with the multi-test static code analysis and CI introduced in the first presentation apply to all wolfSSL products, wolffood, wolfHSM, wolfSSH, etc., or only to wolfSSL/wolfcrypt?
Currently, the fully comprehensive coverage is only in wolfSSL and wolfcrypt. However, a lot of the subtests in that script have already been ported over to GitHub workflows and other test procedures on the other products. So we are slowly rolling it out to the rest of the products. Wolf Sentry does have all of the same test coverage plus some additional coverage. The Wolf Sentry testing program was actually co-developed with the wolfSSL multi-test scripting. So that's just a historical accident that they have similar coverage.
Thank you. And there's another question. Is what are code stems?
What are our code standards?
SHIMS.
Oh, shims. Those are just macros. Sometimes they're functions, sometimes they're macros. But a shim is it's sort of a do nothing macro or function that just maps a particular desired API to an underlying implementation of it. So in the case of xmalloc, we have some build options that allow for deep instrumentation of heap access as a built-in feature of libwolfSSL. The shim allows us to activate those, to write code that properly tracks which allocations are being made and for what purpose. But in the normal build, those extra arguments that are passed are actually discarded. And what the shim does is it discards the extra debugging arguments that are passed into the shim and just passes it directly to the malloc call.
Perfect. And there's another question. Given that AIs don't always generate the same output every time, is there a way to be sure that a previous test is rerun exactly as done before to ensure that a bug is actually fixed?
That's a question for both me and Peter. From my end, I'll just emphasize that you can run for our own fuzz testing. There's certain fuzz testing that we run routinely in our nightly test. And the way we maintain repeatability is we choose a random seed and then the test log actually renders the exact value. In this case, it's a 32-bit integer seed. We render the value of the seed, allowing a subsequent offline test to run with the exact same pseudo-random sequence in its fuzzer harness. Peter, how are you maintaining repeatability? Is it a similar sort of strategy?
Yeah, so we can, now that we see that it was, am I still sharing? I think I am, right? So we can, let's say, check this fuzz test, or we can now run it. So it's a fuzz test that was generated before, so we can just copy paste the name and say fuzz run. Oops, I don't know what I did. I pressed something, right? And then, right. So the fuzz test is there. It can now run. Oh, it actually is the one that had some finding. The Ubisa. Yeah, I see. Let's just keep on running. So we can keep going, right? After it has this initial Ubisa and things, right? We can keep going. So it's the same fuzz test that you rerun and rerun over again. So this fuzz test, they're not like, once you think the fuzz test is good, you can keep running it, right? Then you can, let's say you have a finding, then you would fix the finding and you let the fuzz test run again, and then you should not have any finding anymore, right? So that's the repeatability.
And I think that if the test is only failing, if it's failing non-deterministically with respect to the wolfSSL pseudo-random, it's called a DRBG. It uses a hash function, SHA-256, to generate a random sequence. If you don't recreate its internal initial state, then you'll be non-deterministic. So in the case of, this is another example of where testing a crypto library is particularly challenging. in order to absolutely deterministically recreate the state under which the failure mode was encountered, you need to know what the seed was in the first run and then recreate that seed in the second run. Now, a lot of these defects are going to be apparent regardless of the DRBG state, but some of them may not be. And in that case, you would only be able to deterministically recreate the failure mode by initializing the library with a known deterministically saved seed value, which is that's a special thing for a crypto library.
Yeah, I agree. So I would say some functions don't require this, right? We don't need to fix seed for this kind of fuzz test because it's all deterministic. You get set key, but there are certain functions in wolfSSL library that you certainly have to fix it before you can fuzz it even efficiently, because you get findings you cannot reproduce if they are based on random numbers.
That's right. So like even like the randomness fact, the non-deterministic factor turns up, and sometimes in places you weren't thinking about it, like if you are establishing an AES GCM, so it's a symmetric cipher context, what's called the initialization vector in the AES GCM session is non-deterministic. And if there's some defect in the code that's causing an unaligned access or a null dereference or out of bound reference, you'll only be able to recreate that by setting your DRBG, your internal pseudorandom number generator seed, to a deterministic value that recreates it. Obviously, any key generation is going to have the same characteristic, that it'll only give you the same result if you initialize the internal random number generator to the same state.
I think you even provide some hooks for this, right?
Yeah, of course.
Right.
Thank you. And there is another question. I would have expected more TCOV around 70 or 80%. Is there any reason for this result?
So I guess I'll take this, right? Because it's about TCOV. Yeah. So TCOV in this case, it means total coverage. So the output that you've seen, let me maybe show, because now the fuzzer has done its work and you won't see it. So this was the total coverage. And wolfSSL has way more functions. So because it's a crypto library, it probably couldn't generate proper certificates on its own. So you have to help out. In case of crypto, when you have really structured data, you have to check your fuzz tests and help them out in terms of corpus. So the proper inputs, it has to have certificates and so on, at least in wolfSSL. So you have to make sure that your fuzz test also has proper coverage and you helped it out. By itself, it probably not go deep, right? So you can look at it differently. So if you write a fuzz test for every single function in wolfSSL, you probably get a lot of coverage, right? Because you will cover all the low-level functions somehow, some way. But this is not what you want. You probably don't want 3,000 fuzz tests that are all like doing not much, right? You want to have as few fuzz tests as possible. So what I would do is after 3 hours, I would stop and check which functions are actually nice to be fuzzed. So it needs to be like some extra step after this. So after you've generated fuzz tests, you have to kind of see which ones are good, which ones you want to keep, which ones for which ones you need to increase the coverage. So for wolfSSL, it would be surprising to me if we get 70% coverage right away, unless you like write a fuzz test for every single function in there, which you don't want. But so 15% is actually not bad, given that it has probably very shallow coverage.
Yeah, I think what you're saying is there's a big difference between AI-guided fuzz testing and unit testing. So for our unit testing, of course, our coverage is, I think we're north of 85% on GCOV through the unit test. And that's expected because the unit test is actually, it's like it's over 100,000 lines of code that are human generated and specifically designed to explore code paths accumulated over the course of 15 years of development. So we expect the coverage to be very high there because it's just covering everything. It's covering all of the like null arguments where non-null arguments are expected scenarios, and just all of the sort of boilerplate usual sort of unit testing that you need to do. And that just easily pushes coverage very high. But what Peter's doing is he's guiding the fuzz testing toward exactly the places where he expects. Well, I mean, remember the like cyclomatic complexity, line count complexity, what Peter pointed out earlier in the presentation, which is you know where to look for trouble. It's very easy to have quantitative, objective measures of code complexity. And Peter's strategy is to focus on where the problems are likely to occur. It's very easy for us to have full unit test coverage of simple code. What's hard is full unit test coverage of complex code.
Perfect. Thank you so much. And there's another question. It's not clear to me if code intelligence provides the tool to our developers, or you actually run your tooling on our code and then provide findings.
Yeah, so what we would like very much is that you take our tool and test your code. We can help you to onboard it, to set it up, right? But we of course would like that you do it yourself, because you know your code, and you can add the fuzz test to your pipelines, right? And let them run regularly, so that you regularly, if you change your code, the fuzz test will find if there's a problem, right? So and of course, now that we have recently developed it, we are running it on all sorts of things. For example, wolfSSL, like you let it run, come back after 3 hours, check the findings. It's really cool, and it works on other open source libraries. So we are in the process of evaluating and testing it, as well as selling it. So you can do with it whatever you want on your code base.
Perfect. Thank you so much. There's another question. After getting a valid certificate from LLM, you should be able to get deeper in the source code. Which level of T-curve did you achieve?
Yeah, that's a good question. Yeah. So you see here the lines of code that are supposed to be reachable, let's say 41,000. So after doing that, we still don't get that deep. So it needs more stuff. So I was checking this particular function manually, and I got quite deep. I think we covered about 20,000 lines of code in total. So half of this, but we didn't quite get to the total. So we probably need to let the fuzzer run for much longer. So it's after I've wrote the fuzz test, edit the corpus, you let it run, right? Because that's all you can do, and you let it run with as many cores as you can, so that it gets deeper and deeper.
Perfect. Thank you so much. There's another question. What programming language are supported? We see C here, but how about C++, Go, Java, Python, JavaScript, Rust, and more?
Yeah, also good question. So we mainly support, the AI test agent mainly supports C and C++, just because the address sanitizer is so powerful. It tells you right away there's a finding, right? There is no fooling around with the buffer overflow, and it will tell you. So other languages, we do have fuzzers for JavaScript, and we have, so it's called the Jazzer.js. We also have a fuzzer for Java. It's called Jazzer, but they are kind of standalone tools, right? And yeah. So you can use them on your own, but they're not supported with the AI test agent.
Perfect. There's another question. I believe you said that the AI test agent uses static analysis combined with LLMs to create fuzz tests. Is the static analysis built into the AI test agent, or is it using static analysis result from another tool?
So we use, under the hood, we use Clang tooling. So C-Lang tooling, I believe it's pronounced, right? And then, yeah, so we basically, I mean, I can actually show you the logs. In the beginning, we do the analysis, right? So we see here, scanning the file. So we analyzing the file. So we have all the build commands from CMake, right? And then we use, so it's, to answer the question, it's baked into the AI test agent. Doesn't require any external things, so we ship it together with the binary. So you don't need extra tools for this. It should just work right away, and then analyzes. So it takes the build commands and analyzes every single file as well. So we can have a good overview of what functions are in there.
Perfect. Thank you. And there's another question. What is the applicability to this approach on firmware built by a cross compiler?
I'm not sure if this is meant for testing, or for Daniel, or to me?
It's for you, Peter, and it's very tricky. So on our side, we do the we do a lot of cross compilation in both our CI testing and in our nightly testing, and we run inside QEMU and inside QEMU system in order to and some of it is on native silicon in order to test those embedded scenarios. But it's a lot trickier for you because it's a very complicated thing to be set up in the first place to test in these emulated environments. I think you're just you're running on AMD 64 or maybe AMD 64 and ARch64, but just in a Linux runtime, it's like glibc. It's like the usual sort of easy runtime to target. We have to target FreeRTOS and all of the other like deeply embedded things, and we do that in our CI and nightly testing. But it's a whole different dimension of complexity in the testing harness.
Yeah, I see. Yeah, it's really tricky because until now, so we do have the binaries for like Apple Silicon and the x64 for Linux. We are working on the Windows support, but the cross compiling world. So I imagine some embedded devices, right? So I would not. So we don't support this, but I would need to check the build system. So it's probably doable as well. So all you need is
I will say, Peter, one of the ways that we do it is we have custom builds of the compilers that are cross compilers with the sanitizers. And that allows us to do sanitizing tests of a wide variety of ARM silicon, for example. And that's what you would need in order to be able to do the type of thing that we're doing. And it's definitely a direction that you should be looking at. But by the same token, sanitizer support is basically an AMD 64 and ARM thing. It's and I guess x86. It's the sanitizers don't work on most of the other silicon. So that would be an obstacle to your style of testing on those targets, and you'd have to come up with a different way of detecting incorrect behavior, maybe Valgrind.
Yeah, that's true. Maybe we need to ship our own sanitizers for those systems.
That's one way to go. Just hire 8 more engineers.
Yeah, but I think you can compile it on the regular system, like on your PC as well, right? If you find buffer overflows there.
Oh yeah. And I think what the questioner is asking is really, well, what about bugs that you only see on certain target architectures? We use inline assembly a lot, target-specific inline assembly and standalone assembly code in wolfcrypt. And the only way to test those things, obviously, is to actually target the architecture that brings that code in scope.
Yeah.
Perfect.
That's how we do it.
Thank you so much. There's another question. What is the approximate cost of 9.6 M tokens with OpenAI for the 3-hour test shown?
Good question. So because we don't split right now, we don't count if it's input or output tokens. So you have to assume it's output tokens. And I believe, and don't quote me on this, I think it should be about 10 euros.
Perfect. There's another question. How is the LLM utilized? Does it write the code to use the random generated fuzzing inputs and feed them to the test object?
So the LLM is used to generate the fuzz test. So what you see here, this fuzz test that we were just running. So it generates the code for the fuzz test, and then we run it. So the running is separate from generating, and it's run based on the fuzzing engine. And the fuzzing engine in our case is a libfuzzer, and libfuzzer is the one responsible for feeding it the input data. So we don't use LLM to feed the input to the fuzzer, to the fuzz test. So this data that you see here, this data object, it comes from the fuzzer that is the other AI, the old AI that uses genetic algorithms, not the modern LLM.
Okay, thank you. There's another question. Which platform was emulated for this fuzz test? ARM, PowerPC, MIPS, or etc.?
So this, I have an x86 PC. It's a regular PC. There was nothing emulated, just compiled and ran on the regular laptop.
Perfect. And there's another question. I assume for every PR we need token in the order of several millions, correct?
So PR, I imagine,
what
is it
what
a
is
pool?
that? So I think there's a point of confusion here. You're testing on a complete code base. PR is a change set to that code base, but what you actually test is the code that results after the merge of that PR. So really your requirements in terms of token counts is a function of how much code there is grand total and what level of coverage you're targeting.
Okay, I see. So there are many things you can do. You can generate more fuzz tests. For that, you would need more tokens, right? But you can also stop here and now improve the coverage. So you spend some time improving these fuzz tests, increase the coverage by getting better corpus, maybe use another AI to generate it, and then you increase it, and then you see how much coverage you get, and then you can decide if you want to spend more tokens or not.
Yeah, there's an implicit question in that that viewer's PR question, which is, do you have an easy way to focus the attention of the process on the code that was changed by a PR? So a PR is a change set. It's a pull request. So can you focus
okay.
the system on the changed code?
Okay, this is a cool feature. So I guess you would have to do it manually and see which functions are affected. Yeah, we could provide something like this actually, because all you need is you figure out which functions are affected, and then calculate all the way to the top which functions are calling those functions in the whole code stack. We do that already, so we can just maybe take a look. Yeah, it's a nice idea.
That would be a really good feature. And using, I mean, all you'd need to do is like get a little bit of post-processing of the output from git diff. That'll show you like which lines of code were changed by the PR, and then you can do indentation driven testing to discover which functions were being implicated by the changes.
Oh yeah, you can do a lot of things with Git and repositories. You can even track who just added the change. Sometimes.
Oh yeah, we do that. Yeah. Our nightly results. Yeah, we auto label which engineer changed the line of code that was implicated by a Clang tidy defect report. It's just right there, saves us the time, and it, as you say, it's very easy to automate.
Do you have statistics on that internally?
No, but that's a good idea. Although to be fair, it's like that would quantitatively punish the people that write lots of code just because their code is just statistically likely to get implicated in the call stacks. So you have to be careful about like creating perverse incentives.
But you could totally do that for a fuzzer, because there it doesn't matter. It has no implications on the people. You can just anonymously target for better better results.
So Edwin is asking about testing interrupt handlers. I think I know the answer to that, Peter. Do you want to take it, or do you want me to just explain why that's not yet something that it's equipped to do?
So I don't understand the question. What does it mean, fuzz test interrupt handlers? So it's like an exit handler?
This is bare metal and kernel stuff. Interrupt handlers are the internal. So when there's a hardware event on a platform that causes the hardware to automatically vector to handler code. But this is internal kernel mode hardware stuff. And your debug loop that your AI runs in has like UBSAN and ASAN in it, and you don't run those. I mean, there is such a thing as the kernel sanitizer, but no, that's not the way your harness works right now. So the way to debug interrupt handlers is manually and with existing static analysis tools, and just by handing it to an LLM directly and asking the LLM if it sees anything wrong with it, and using your genetic algorithms and auto-guided fuzz testing strategy on something like that's a future capability, not a present capability.
Okay, so I would answer it maybe a bit diplomatically. If your fuzz test is able to detect interrupt handlers, right, then you can use fuzz test, right? So if it's possible to detect them, right, then it's just a libfuzzer fuzz test. There's nothing special about it. So the AI loop that I've showed to generate a fuzz test is independent of what you can detect, right? So if you can manage to detect them, it should be possible.
And you know, Peter, that's a better response, because they can use QEMU's system in order to create a runtime where, in principle, they would be able to detect it. And that's what we do. We use QEMU. We run sanitizing kernels under QEMU's system, and that allows us to build a test harness around testing things like that.
Perfect. Thank you so much.
Can I ask you, Daniel? Maybe it's possible to ask you. Do you have fuzz test running in QEMU?
Yeah, we have some fuzz testing. One of the things that we fuzz test is, so when you're running inside the kernel, you cannot count on the availability of the vector registers. So we have to dynamically fall back to C implementations of some of the cryptography, and we fuzz test that. And that's one of the things that we do have running under QEMU's system inside the kernel, is fuzz testing of C fallback, which that exercises a lot of the resilience of the code base around structure sizes and correct results from the cryptography.
Interesting. Thanks.
Sure. We also use the Linux kernel has built-in cryptography fuzzing, and we do use the Linux kernel's built-in crypto fuzzer. But I mean, basically, it's just fuzzing different initialization vectors, keys, and plain text and ciphertexts. So it's not fuzz testing like you're doing. It's fuzz testing for algorithmic correctness. But that's a second type of fuzz testing that we have running under QEMU's system inside the kernel.
Cool.
Thank you so much. And there's another question. What is the difference between a unit test and a fuzz test? Like in terms of possible inputs?
Yeah, so a fuzz test, so a unit test just tests for one thing, right? You have, you usually write unit tests that are very self-contained and very limited in what they do. So they test just one thing. In case it fails, you know exactly what's happening. And a fuzz test is, so here, since I have it open already, this data that comes from the fuzzer, it's so wide, so various, so much different data that comes through, and it runs through all these functions that are called in the fuzz test. So you can imagine a fuzz test is like a thousands of or even millions of other unit tests in things that it tests. So here, for example, this fuzz test has 277 kind of corpus entries. So unique test cases in this case. After running the one that I started after, so it ran and it finished, and it has 277 unique test cases, and that means that each of these unique test cases reaches different parts of the code base. So there you have it, 277 unit tests in this case. It's kind of dynamic unit tests.
Perfect. There is another question. Do you have a comparison of the new AI approach compared to further like AFL?
So yeah, maybe I have to again separate the fuzzing engine from the AI. So the new AI approach generates the fuzz tests. We also support AFL. So the fuzzing engine that runs underneath is just used to run this fuzz test that was generated by the LLM. So there are two different concepts. But so you cannot. So they're completely different. I don't think I can compare them, right? So we generate fuzz tests with the new AI and let them run on the old AI, which is libfuzzer or AFL++.
Awesome. And the last question, do you support Linux on ARM?
Not
Yes, we
sure who
do,
that
actually.
question is for. We both, it sounds like the answer is yes from both of us.
From both
And in
of
fact,
us.
we
Yeah.
support the Linux kernel on ARM also, on the wolfSSL side.
Perfect. Thank you so much. And thank you, Daniel and Peter, for hosting an informative webinar. And thank you, everybody, for joining the webinar today. And you can keep up with our upcoming events, meet our team in person, read our blog post, and get the latest wolfSSL and code intelligence updates by following us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. If you have any question, please reach out to us at fax@wolfssl.com. Thank you again, and we look forward to seeing you on March 6th for Core Roadmap 2025 with Daniel Stenberg. Thank you so much. Bye.
Thanks, Shizuka. Bye.
Thank you. Bye.